So we resume our exploration of Bellman Ford and distance vector. We have seen so far the centralized version of Bellman Ford and how resistant it is to initial condition, to strange initial conditions. Now what we would like to do is to do it distributed. Distributed means we really apply the message passing approach by having every node send to its neighbors the current value of its estimate of the destination, of the cost to destination. And asynchronous means every node sends it independently of each other, which means that some node may be fast, they may send 10 updates per second, whereas others might send 1 update every second. So the nodes are not progressing with the index k being the same for all. That's the main difference. That gives the following algorithm. Every node maintains an estimate of the true distance, which I call P, Q being the estimate, to some destination, to node 1. It also keeps a record of the latest values received from all neighbors. The initial conditions are arbitrary, but of course at node 1 always says it is at distance 0 of itself. And from time to time, a node sends its value, its estimate of the distance to the node 1, it sends its estimate to all neighbors. Hopefully you do it not just from time to time, but frequently enough so that you don't have to wait forever for an update. And of course, if all your neighbors do that, you receive updates from your neighbor. So what do you do when you receive one update from one neighbor? When I receive an update from a neighbor, let's say J, it receives the estimated value Qj from its neighbor J, then it does the following. It applies this equation. It will compare the value of all the last received value of Q from all neighbors, which it adds to the cost of going to that neighbors. So it can do that because the Q is either the one you have just received or for the other ones, the one you have stored, because you keep in memory the value of Q for all neighbors. And you redo this minimum computation. Sometimes receiving a new value of Q will change the value of the minimum, sometimes not. In any case, you update Q by saying you take the new value. If this doesn't change the value of your Q, then nothing happens. If it changes it, then you update it by putting Q of R. So this is exactly the message passing interpretation of the centralized Bellman Ford. Why is it? Because the centralized Bellman Ford is saying, I do the minimum over all neighbors of the Aij plus the Pk minus 1. So here we say we do that, but of course we do it only when something changes. When does something change? When we receive one update from one neighbor. So we have the Q, which is morally speaking the vector of the Pk minus 1, and then we take the minimum, and this is our best estimate of Q. Of course, now what is a bit weird is that the index k is not the same for everyone. But that's the best we can do if we do it asynchronously. Once we have done this, then if we are lucky and the Q are the true values for P, then we can compute the next hop by saying, whenever I do that, I not only compute the mean, but I record what is the index j, what is the neighbor j that achieves the minimum, one of the neighbors that achieves the minimum. And then I set that to the next hop. Next hop means where I should send a packet to destination 1 from myself. This is also common sense because we saw that once we have Bellman Ford that has converged, we can recover from the distances the way to go to the destination by taking the neighbor that achieves the minimum in this. Of course, what is happening here is if this algorithm does not converge, or if it converges and it has not yet converged, the destination, the direction we're giving to go towards 1 might not be the correct one. This happens in the internet. When we run distance vector routing, all nodes do this, or a variant of this that we'll see a bit later. And if the thing is not yet final has not yet converged. Perhaps the directions are not the correct one. And that might even cause routing loops. But fortunately, we know that routing loops will not last forever. And even during the presence of routing loops, the TTL will take care of killing the packets that are caught in the loops. So this version, I call it BF, Bellman-Ford preliminary. It's not the one that is truly equal to distance vector routing. But that's what we obtain if we apply a centralized algorithm, which is synchronous with synchronous loops and iterations, in an asynchronous way. That's a very powerful method to do distributed algorithms. So many distributed algorithms are based on this way of doing. First, you do an algorithm down on a graph, then you try to interpret it by having local exchange of information, and then you remove the synchronicity that existed in the original algorithm. If you're lucky, that gives a good distributed algorithm that will work. Are we lucky here? Yes. If we put enough safeguards. The safeguards are, well, when nodes send updates, first they should not wait forever for sending updates, and you should have a guarantee that you will receive the updates. So if messages are lost, then you repeat them, and in a finite number of repetitions, you're certain to receive the update. So if you assume those elements that I said, the algorithm will do exactly the same as Bellman-Ford centralized. So more precisely, then if at least one message is reliably sent to all neighbors by every node every t time units, and if the network is fully connected, then this algorithm converges to the same result as the centralized version, namely to the correct values in a number of steps, which is bounded by the time unit times the number of steps that the centralized version would have taken. So in other words, if some nodes are faster than others, for example, if they send 10 messages per time unit instead of 1, like is required here, it won't hurt, which is easy to understand. In the small simulations we've seen in the first hour, we've seen that things only get better. So if some nodes are faster, then they, in fact, locally accelerate convergence. This is one way we can interpret this result. So Bellman-Ford is very robust, and if some nodes are faster, then it will locally converge faster. Perhaps globally it will not improve things, but it will never hurt. Voilà, so that's the first good news. Distributed Bellman-Ford works. Here is, for example, a small simulation. I'm showing an initial state. So that's the information that this prelim Bellman-Ford needs to keep. Q, that's the value, the estimate of node E, plus it needs to remember the estimates of the neighbors. So assume the neighbors, he has heard nothing from neighbor B, which is equivalent to having no entry or having one entry with the value infinity. And from C and D, E has heard the values 7 and 3. Now assume B sends a message to E. It sends its value, which is 1. Then the node E changes its value and redoes the computation by comparing those 3 neighbors now with those new values and find which one is the best. Now, which one is the best in that case? Well, this new value gives me 3, and the previous I had before was 4, so this is better than what I had before. So it must be better than the 1 I had here. So my new value is 3. And if I examine more closely, it also tells me that the neighbor that achieved the minimum was B. So I should route via B, and the distance is 3. This is showing here the value of Q at the different nodes in this, at this time in the evolution of the algorithm. And then we can continue the simulation. We could see, for example, sooner or later, E will also send a message to B with its new value, because now it has changed from 4 to 3. It will inform the neighbors. Nothing will happen. But E will also send the information to C, and this will help node C, which thought it was at the distance of 7, to discover that now it has a better path, which is at the distance of 4, and at this point, the algorithm has converged. So this is distributed Bellman-Ford, I would say, as a straightforward application to making it distributed and asynchronous. Now we would like to do better And in particular, what we don't like in this algorithm is the fact that E needs to remember its distance, its best estimate of the distance to node 1, but also the best estimate of the neighbors. Right? If we would do that in the internet, that would mean a router needs to have its routing table and the cost to neighbors, but also all the routing tables of all the neighbors with their costs to all the possible destinations. If we have to have that, well, let's have it. But if we could avoid it, it would be better. So let's try to avoid it. Let's try to do an algorithm that would keep only as information its cost, its own value, Q, which is the estimate of P. This is what I call super duper, right? Because we've dramatically reduced the amount of information. So super duper would do this. Well, all I do is keep value Q. Then when I receive an update, what did I do in the previous example? I compared the update to the value I had before. So let me do that. All I need to remember, of course, the update I've received, I keep it, but I will throw it away as soon as this computation is done. I receive from a neighbor J an update. I compute the cost of going from me through J to the final destination. That gives me this. And I compare to what I had before. And I take the best of the two. Right? If I do this, then bingo, I should do the same. And I have avoided the need to keep the value of Q of J. Does it work? So this is the third instance today where I ask you to just follow your intuition and see what happens. So 5 more seconds and I close. And the correct answer is is 2. It works, or perhaps not only, but of the 3 answers, that's the best one. It works, but not in the general case. It works if the initial conditions are the natural one. If we start the algorithm and we assume there is an initial condition, which is very hard to assume in a distributed algorithm, other than when we do it in a simulation, but in real life, we don't reset the internet and say, okay, all distance vector routers, please start from those initial conditions. It's hard to do. In fact, it's impossible to talk to routers before you have a routing algorithm that has converged, because in order to speak to the routers, we need that the routing tables are correct. So we have a chicken and egg problem here. Why is it so? Well, we can see why it doesn't work in general. It is because this update takes the minimum of what I had and of the new information received. So it can only decrease. Right? So my estimate of the destination, I am node I, my estimate Q of I, when I receive a new update can stay the same or can decrease. So with this algorithm, it can never increase. Now, if I start from initial conditions that are below the true value, certainly this algorithm cannot converge to the true value. We have seen examples in the first hour that with the centralized Bellman FD, we could start with nodes that believed they were at a distance of 1 of the final destination because of bad initial conditions, and the true value was much larger than 1. So if this happens, this algorithm is impossible to converge. It will take seriously those guys saying, I am at a distance of 1. So it cannot work. So super duper is not so super duper, in fact. Now, if we're interested, but this is highly academic, if we're interested, we can show that it works if we can guarantee that the values are initially high enough. So ideally, if they're infinite everywhere except 0 at 1, then the algorithm can only decrease. If the topology doesn't change during the execution of the algorithm, then it will converge. But of course, we should not rely on this in the internet, because in the internet, there is no guarantee while we're running the routing algorithm in an asynchronous manner that changes will not occur. So in practice, super duper is not good. Here is the true version, which is a bit subtle. It's hard to understand why we get this, except if we do all the steps we did now. So the true version keeps the idea of keeping only Q of I. So node I keeps only Q of I. However, it also keeps another information, that's the only Q it keeps, but it keeps also the information where to route, which is the job of any router. Right? So Q of I has, the router I has two information, Q of I, its best estimate of the distance to the final destination, and where to go, next hop of I towards the destination. Then if we run this algorithm with any arbitrary conditions, but of course we need to force that node 1 always says it is at a distance 0 of itself. So with any arbitrary conditions, and then from time to time, as before, we inform our neighbors of our value, Q of I. We don't need to inform a neighbor of where we route, just the value of Q. And then the update is a bit changed. When I receive an update from J, I treat differently the case where J is the next hop. So if J is the next hop and sends me an update, Q of J, I adopted it. I take it without discussion. I say my new value of Q of I is the value that J is telling me plus the cost of going from me to J. I do that only if I receive an update from J who was previously for me the best direction to go towards the final destination. Otherwise, if I receive from a J that is not the best the next hop, I do what super duper did. I compare what I have to what I would have if I adopt this one. So this is what I call Bellman FD distributed. So we take super duper, except in one case, if the message is coming from what we consider before the message as the next hop, we take this message seriously without discussion. This gives a mechanism to increase, possibly, because now here we can only decrease the value of Q. Now, depending on what happens here, the value of Q might change and might increase. So there is some hope that we break the bug of the previous algorithm. Let's do a simulation here. So I am at node E. Node E believes at some point it is at a distance of 1, which is completely wrong. And it believes that the next hop is C. Right? Perhaps because C in a previous life said it was D or what it was the destination or whatever. Then let's assume that C sends a message to E saying my destination is, so why do I write 1 here? It should be, C should be 1 on the figure. I think it's a bug. It should be 1 here, not 7. So E received this message from C, and C is the next hop. So E will, so this is not 5, but E will do the update and adopt it because it comes from the next hop. I will say my cost to the final destination is 2. No discussion. Right. So here is the change of state for the array of all the estimates. Node E has changed his opinion by receiving this message from C. Now, if we continue and at some point we get to this value with the same bugs here, it is 1. It is 1 in this box. At this stage, E believes it is, for example, a distance of 4 for whatever reason. If it receives a message from B saying I have a distance of 1, then B is not on the shortest path, so it will compare. Now 2 plus 1, 3 is better. so therefore it will adopt it. B becomes the next hop, and this is the update that will happen here. So I've illustrated here how the algorithm works. Now, what is hard to believe, but is true, is that this correction is sufficient to break the impact of wrong initial conditions. In other words, it is correct. With the same conditions, of course, we need that there is a bounded time during which every neighbor is able to send to, every node is able to send to all neighbors an update with 100% chance of being received. And if that happens, then the algorithm will, in a finite time, converge to the true value, which is the correct distances. Voilà, that's about the theory. We'll see the practice in a few more minutes, but if we summarize everything we've seen, Bellman FD distributed allows a node to compute distances to one destination by storing only the next hop to the destination and the distance to destination. It works by message passing. Every node informs its neighbors of its current distances only. If we have only one destination, every node informs of a single distance. And it works whatever the initial conditions, which is very important for a practical asynchronous operation in the internet. In particular, wrong initial conditions correspond to probably final conditions that were correct before something changed in the network. Topology change, we've added a router, or we've added a link, or we've removed a router or a link, or something has crashed, which, as you know, happens all the time. If, now a small caveat, if the destination is unreachable, then the algorithm will also correctly count the distance, which is infinity, which means it will increase to infinity. So it will exchange messages, and the values of the messages will increase forever, which of course needs to be handled, but is in theory the correct thing to do. Voilà, that's our end of the theory part of distance vector. Now, how is it done in practice? In practice, it's a direct, straightforward application of what I've said with one or two bells and whistles that we will see also. However, the first important thing to realize is that we don't compute paths and distances to one destination, but to all possible destinations. What is a possible destination in the internet? Well, it's a prefix. It's a network prefix, like for example, 128.178/15, which means EPFL. So if we take a graph theoretic view of what distance vector does, we have to imagine that there are nodes that are routers, but there are also nodes that are prefixes. Other than that, we do distance vector, for example, using exactly what we saw. So node I, which is router I, will send to all of its neighbors its estimate of its cost to going to all possible destinations. So if n is a destination prefix, this router will send to router 1 the cost of going from itself to n for all possible n, and vice versa. I will receive from all neighbors all their estimates of their costs from going to router n, and of course the routers need to be configured with the cost of going to the neighbors. So we need to configure what is called the cost of links. For example, in RIP by default it's 1, in which case the distance is simply the number of hops. Now, if we interpret it as a message passing algorithm, what is a router doing? It is sending to its neighbors the costs for all possible destinations. This is the famous vector of distances. This is why this is called distance vector routing. We pass messages which are the distance vectors. And by only passing these messages and running Bellman FD distributed, we converge to the correct shortest paths. You will see in the lab RIP that does periodic updates. So it sends it does literally what I said before. It sends the updates, even if nothing changes. It will send the updates, for example, by default every 30 seconds. Or if something changes, then you send immediately an update. The distance is sometimes infinity, which may be visible in a routing table or the routing information base. So routing information base, RIB, is, in the context of a routing protocol, the information that the routing protocol uses. Distance vector, in principle, uses only the routing table. If we add to the routing table the cost of going to the destination. But very often, and that's the case for most of the ones we will use, it still puts that in its own private information that replicates the routing table. If a node is unreachable, it can be visible in a routing information base by saying the distance to that node is infinity, but most of the time it is visible by being invisible. In other words, if a given destination prefix is not present in your list, that means its cost to it is infinite. This is how we interpret infinite costs, because we don't have an exhaustive list of all the prefixes in the internet. So here is a small example that is simply translating everything we've seen to the language of IP and routers. I have a toy network like we do in the lab with 4 routers and 7 subnets. Some of the subnets are the links between routers. Some of them are final subnets, M1, M2, M3. And what will distance vector do in that case? Well, initially, you need somehow to discover which are the directly attached subnetworks. You do it that either using some automatic software or in the lab we'll do it manually. So for example, C is configured with 4 interfaces and the corresponding subnet masks and subnet prefixes, so it knows that it is directly attached to itself to those 4 prefixes. So in this case, it says the distance is 1. You need to check what your software does. So here, for example, this is the initial information at C. I am connected to N2, and the next hop to N2 is via N2 and via me, which is a complicated way of saying it's on link with me. And that's the only information we bootstrap into the network. We need to bootstrap this. I mean, somewhere we need to say what are the prefixes that exist. For example, A has only 2 prefixes, N1 and N4, and then they do distance vector. So distance vector says, I am sending to my neighbors my costs. For example, A is saying to B, I have N1, I am at a distance 1 of N1, and similarly of N4. So if we think of the Bellman FD message passing interpretation, we have 2 messages if we want, because we have 2 destinations. But of course, in the routing protocol, you will try to pack as much information in one packet, not send 1 packet per message. When B receives this, he does the Bellman FD computation. So for N1, so B thinks it has received 2 messages. So it will handle each of those lines as if they would be separate messages. So I look at N1. I see N1. I'm receiving a message. Is it coming from the next hop? Answer is no. It's no. Or here, depending how we treat the next. Yes, it is coming from the next hop because that's the interface through which I'm routing for N1. Would I say that? No, it's not coming from the next hop because the next hop is myself, B. So I compare to what I have. Of course, it's less good. So I ignore it. Similarly, for N4, I compare to what I have, which was nothing before. So nothing, I interpret the distance infinity. This guy is saying he's at a distance of 1. Here all the link costs are 1. So that gives me a distance of 2 here. So this is what Bellman FD will do. And similarly at C, so we see that after receiving 2 messages, the routing tables are growing. And then the next thing will be C will send all of this routing table to B and to D. And now B and D will compare for each of those 6 lines what they have. They will say, is it coming from the next hop, in which case I adopt it, or not, in which case I compare to what I had before. And in this way, for example, C will discover from B a path to N1. And perhaps even to N2, if they, no, it has already a path to, from N1. So this is being illustrated here. So how C sends to B. So we see that B, for example, will discover the existence of M1, M2, M3, etc. You can easily imagine. I skip the steps. In whatever order it happens, it doesn't matter. We've seen that the correctness of Bellman FD distributed says that at the end we will have this. We will have the correct distances, which, for example, for D, say that the distance to M2 is 2, and the next hop is C, which is correct. In order to go from D to C, I go here. And from A, the distance to M2 is via D, and is 3. Now, A had 2 alternate paths to M2. It has picked one of the 2. Yes?
If you go 2 slides back, yeah, when you wrote from D, N3 0, N4 0, M3 0, I don't understand why there are zeros.
It's 1. It's a bug. It's a bug. It's 1, 1, 1. Yeah. Thank you. Okay, I can't write on it. Now let's check that the Bellman FD property, which is ability to resist to wrong initial conditions, is translated into resistance to topology changes. So assume a link fails or a router fails, so A crashes. It's caught in a loop, doesn't respond. What will happen? Well, with a protocol like RIP, the nodes are supposed to send an update every 30 seconds. So when the neighbors don't receive an update, then they consider that for 2 or 3 times, they consider that A has crashed. So by considering that A has crashed, B and D are now informed that A has crashed. What do? Well, they interpret that by saying anything that was coming from A, so anything that was saying the best route to this destination is via A, is now invalid. So I do as if had sent to me the information, my distance to those nodes is plus infinity, which you can do in 2 ways. You can write plus infinity in the table, or you can delete it. So here the net effect is B and D have each deleted the entries that corresponded to what was said by A. Which in fact means now that D doesn't know how to go to N1. So if there's a packet to N1 happening just now, it will be lost. Right. Of course, there is an alternate path to N1, which is via C. But now, what will happen? Well, we will continue running Bellman FD. This algorithm never stops, the distributed version. It will never stop. It continues, but now it continues from the state that is here, which correspond to wrong initial conditions for this topology. There is wrong initial condition, for example, because someone might believe that might route something via A. It might be, so, well, it's not the case here, but it might be depending on C. Yes, the choice of C, for example. C, no, there's no impact here, other than those infinite conditions and the others that are based on the previous conditions. So we know now that it will converge to the correct new value. And we can check this here. C will send this distance vector to D, and D will now get a new information about N1. C says it is a distance of 2, therefore D learns that it is a distance of 3. And similarly, B will receive information from C that will teach it that in order to get to A, it should go via C, in order to get to N4. So it's a simple example where the thing is repaired very quickly, but the take-home message is topology changes correspond to failures, and with distance vector, when there is a failure, there's nothing to do. We simply continue running the algorithm and it will get back on its feet. Of course, you need a quasi-stationary assumption here. If the network changes more frequently than it takes for the algorithm to converge after a change, then the system will not work. If there's a crash every second and with RIP, it will not work. So because RIP needs perhaps 2 minutes to converge. So it works as long as the changes are not too frequent. Now, a network in which you would have a router that comes and goes every 1 second probably needs to be fixed by changing the router. Now let's see a few optimizations we need to do compared to that. So here's another example with 5 nodes and links and prefixes A, B, C, D, E, etc. And assume the network has converged after the algorithm has converged after some time to this value here. So for example, we can check that node A routes to prefix E by going via link L3, which means over this interface, and is at a cost of 3, 1, 2, 3. Assume now you break simultaneously link L1 and L6. Of course, you could tell me that the probability that that happens is 0 because Poisson processes, whatever, the probability that 2 events occur at the same time is 0. That's true in some setting, but in networking we don't make this assumption for various reasons. I mean, first, it's maybe true that they don't collide, they don't crash at exactly the same time, those 2 links. But at the time scale of the routing protocol, which is a fairly slow time scale, it might more or less be at the same time. So the 2 might be cut within the same interval between updates. Second, there are many reasons for links to break together. There was, for example, a few years ago, a fire in a tunnel. There's been fires in many tunnels, but there was one in a tunnel in the city of Boston between the airport and the mainland. And inside this tunnel were all fibers of all American operators, except US Sprint. And worse than that, in fact, there were multiple links, like exactly L1 and L6, were both going in the same tunnel, in different fibers, in different plastic tubes, but in the same tunnel. When the tunnel burnt, everything melted, and you lost the 2 links at the same time. Assume that happens here. What will happen in our distance vector algorithm? Well, sooner or later, this guy here, D, that was routing towards E for destination C, for example, will detect that this link is down because those 2 routers speak together. Remember, a routing protocol is not routed. The packets of a routing protocol are not routed. They are sent to a router, and the router processes them, does its Bellman FD stuff. But they're not forwarded by routers, so they always go only one hop. So there is a hello or an update process between D and E. When the link goes down, certainly this is detected by absence of those updates. It can also be detected in other ways. For example, if you break your Ethernet cable, a LED will stop lighting, blinking here, so your operating system can detect that the link is down. So whatever the reason, D detects it, and then, as before, kills the entries that were pointing towards E, which is intellectually the same as saying, as if I had received from E the information, those distances are now infinite, which is a way of doing what we call Bellman FD distributed. The next hop was E. If E is down, then we adopt what the next hop is saying, which means now it's infinite. Then we continue to zoom on what happens on A and D, which are now isolated. Assume now A has not done anything. It has not detected the loss yet, perhaps because the loss will be detected by absence of hello or update messages. So it will happen later at this part of the network. So A sends to D its routing table, which is prior to the failure. So it's an old, completely obsolete and wrong routing table. We shouldn't be worried. We know that's exactly what Bellman FD is robust against. If you start from initial conditions that are inherited from a previous situation, it will continue to work. So what will happen here, A says, well, I am at a distance 1 of 1, which is correct, but at a distance 3 of C and E. Then D says, oh, wonderful. Now I've recovered a way to go to C, which is now via A, link 3, and the distance is 4. Of course, this is completely wrong. But the next step, so might be, for example, that A detects the failure and then gets the update from D. This update, of course, was poisoned by the wrong values that were sent from A before the failure. So D is now resending to A what A had said before, which now A is happy to say, oh, now I have a link to C, which is at a distance of 4 plus 1 equals 5. If we continue this game, what do you think will happen? So, for example, if D is in this state, blue, and receives the red update, what will the distance to E be after this update? Five seconds. I think it's a simple exercise. Five more seconds. And the correct value is, of course, 6. You recognize here, you recognize, in fact, exactly what we had done before in the context of a graph, now in the context of a network. We have, 49, 50. The distance is 6. It simply applies distributed Bellman Ford. The update is coming from the next hop, so it's accepted, and it is 6. Well, in fact, what will happen is that this distributed Bellman Ford does exactly the same as centralized Bellman Ford, and we've seen what centralized Bellman Ford does when the network is disconnected. It counts to infinity. So this will happen here, and we can do a simulation to see. We see that the distance to C, for example, grows 6, 7, 8, 9, 10, etc. They will increase forever, which is the correct thing to do. The distance is infinite. Now, what do we do in practice? I mean, you're running your router in GNS3 in your VirtualBox, and then it's going to 1, 2, 3, 6, 8, 10, 12, etc. The true answer is, at some point, it's not reachable. Destination C is not reachable in this network. In practice, this is, well, you need a way to catch it. There are different ways to catch it. The simplest way is to say, well, we put a bound. So in RIP, for example, infinity is 16. So if you reach 16, you say it's infinite, which means that RIP is designed for a relatively small network where the number of hops you go from A to B inside the network is never more than 16. So this is one of the direct application of what we've seen before. And again, I'm stressing count to infinity is not a bug, but it's just a desired property of the Bellman Ford algorithm that is truly computing an infinite distance. Now we can still avoid count to infinity by a number of, in some cases, a number of optimizations, 2 in particular that we'll see that are very visible in RIP, that are called route poisoning and split horizon. Those are just 2 common sense rules that say route poisoning says instead of silently discarding a route that's infinite, when a router has an infinite route to some neighbor, it will actively send the information route my distance is equal to infinity to the neighbors. So that will, as we will see, that will accelerate the convergence. And second, split horizon, which is just a common sense rule, is say, well, if one neighbor says, I am the best to go to that, here is my distance to that destination, and if I consider that this guy is the best, so if A routes packet to destination X via B, then A does not announce this route to B. Right? Because if I go via B, that means B knows a better path than what I know, because I rely on the path of B. So I should not send that information back, which will stop the ping-pong game, at least in theory. Let's see in practice why this works. So we see the same case as before. We break the links, and we restart at the time when D has detected the break. So D detects the break, it detects that C and E are no longer reachable. Therefore, B will send an update to A, but now using these heuristics, those two heuristics, there will be two changes to the update. First, in the previous case, D was sending nothing about C and E. It was saying, I don't know. Now it will effectively send the value infinity. And second, it will not send information about A and B, because A and B are routed via A. So it will not send this information. Last slide of the day. What will happen after that? What will happen at node A? So node A receives this update. If it applies Bellman FD with all the bells and whistles we've seen, what will be the result of the computation? I close in 5 seconds. And the correct value is number 3. Let's see why. A applies Bellman FD distributed. That says you should separate whether the update comes from the next hop or not. So for C, destination C, before receiving that, the next hop was somewhere here in this direction. So I receive an update from B saying I am at a distance infinity of C, but it's not the next hop, so I compare to what I have. What I have was a better distance, so I ignore it. So 3 remains unchanged. So after receiving that, A will still believe wrongly that it is at a distance 3. However, for E, distance E that was routed via D, A was sending to B in order to go to the destination E. Now B says the distance to E is infinite, therefore A will adopt that without discussion and will set it to A. Therefore the correct answer was 3 infinity. And the majority is not always right, as we learned today. Thank you very much. We will be able to explore this in the lab tomorrow and